Good morning, good afternoon, good evening. I don't know when you're watching, but thanks for watching. We are covering section 11.5, decomposition reactions. This is a continuation from yesterday. When we started talking about types of reactions. Yesterday was all about combination reactions, where you have elements or small compounds creating a larger compound. Okay. Always when you have a synthesis reaction or combination reaction, you'll have two reactants or multiple reactants creating one large compound. Okay. Today is going to be the opposite of that. We are going to start, instead of having two reactants or more than two reactants, you're going to have just one reactant. One large compound is going to break up into multiple products. And of course, those products can be compounds or elements. It just depends. All right. So, how does a decomposition reaction work? We're going to start today's lecture talking about Antoine Lavoisier. All right. So, who's going to help me with the introduction? Thanks. Anthony Lavoisier. 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 Wait, say it again? Lavoisier. Lavoisier. It's widely known as the father of chemistry. He was able to study to Lavoisier ran mercury with oxygen to form mercury oxide as part of his studies on the composition of the atmosphere. He was then able to show that decomposition, the composition of the atmosphere, the composition of the mercury oxide produces mercury and oxygen. The diagram above shows the materials used by Lavoisier to study the formation and decomposition of mercury oxide. Thanks. Thank you so much. A lot of very large vocabulary words, right? It can totally get a little bit tongue twisted. But the whole thing is that Lavoisier was one of the first to study this type of reaction. And he studied the breakdown of mercuric acid. And you can see the device he used, okay? And I'm not really sure, but it looks like this is a power source, and this is actually where the reaction occurred. I don't know. Or it could be the other way. Maybe this is where the reaction occurred, and this is where they trapped the oxygen. I don't know. The main thing that we need to know is that he was the first one to study this type of reaction. So a decomposition reaction, like we said, is a reaction where you have a large compound breaking down into two or more smaller compounds or elements, okay? And the general form of a decomposition reaction is shown, okay? Where you have a compound composed of element A and element B. Remember, these are just generic forms. They're talking about any element on the periodic table can break apart into its elements, just like you see it here, element A or element B. But it doesn't necessarily just have to be elements. It can be compounds as well. The first thing, most of these types of reactions require some form of energy in order to occur. And that could be in the form of heat, light, or electricity. So it's going to require for you to apply some type of energy source. Binary compounds are compounds composed of two elements. This is the simplest kind of decomposition reaction is when a binary compound decomposes into its elements. For example, mercury 2 oxide, the same type of reaction that Lavoisier was studying, is a red solid that decomposes when heated to produce mercury and oxygen gas. So you can see that this small compound is breaking down into its individual elements, right? And this reaction requires 2 moles of mercury oxide, and you're going to produce 2 moles of mercury in the liquid form and 1 mole of oxygen in the gas form. And here's a picture of what it looks like before it decomposes. And it basically looks like sand, right? It looks like a fine powder, a red-orange powder. So here's your first Pear Deck question, guys. And it says, or it's asking, sorry, which of the following reactions is considered or is a decomposition reaction? Circle your answer. So you have 4 options, right? Option 1, option 2, option 3, and option 4. Which one of these is a decomposition reaction where you have a large compound breaking apart into smaller compounds or elements? What do you think? Ms. Diamond, what do you think? Which one do you think here is a decomposition reaction? Irvin, Oscar, what about you? Which one do you think looks like a decomposition reaction? Number 4? Thank you, Ms. Diamond. All right, so she's saying that number 4 is a decomposition reaction. Let's check it out. Calcium carbonate, CaCO3, definitely is a large compound, right? It's a large compound. It's a large reactant, right? One reactant is breaking apart into smaller compounds, right? Or smaller products. One reactant, 2 products, that is definitely a decomposition reaction. Very good, ma'am. Oscar is saying that number 2 is another decomposition reaction. All right, let's check it out. So we have lead 2 sulfate. One reactant is breaking apart into into a small compound and an element. Very good, Oscar. You are correct. It used to be lead 2 sulfate. Now it's lead 2 sulfite. One of those oxygens has breaking apart and escaped, right? That oxygen, that diatomic oxygen has broken off. It's okay, Mr. Jeremiah. All right, so if we look at number 1 and number 3, we can easily eliminate them just by looking at the reactants, right? Number 1 has 2 reactants. That's out. There's no way it can be a decomposition reaction if you have 2 reactants. Number 3, the same reason, right? The same thing. The fact that it has 2 reactants eliminates it. But also, look at the product side. We don't have more than 1 product. That's also a red flag for us, right? The fact that there is only 1 product tells us that it is not a decomposition reaction. This is actually the type of reaction that we talked about yesterday, a combination or synthesis reaction. We are creating from 2 small compounds a large compound. 2 reactants, 1 product, that's synthesis reaction. That's what we talked about yesterday. Very good, guys. Very, very good. Excellent. Excellent. I agree. Very good. Here, let me give you the link, Jeremiah, in case you want to join us. All right. Irvin got here. Jeremiah. Let me just change Jeremiah. Okay, Jeremiah's. You already counted present. Okay, perfect. Let's move on. So now we're going to talk about some more examples of decomposition reaction. A reaction is also considered to be decomposition even when 1 or more of the products is still a compound. All right. So it's not always going to happen that your compound will break up into elements. It could also break into smaller compounds. Okay. Just because you have a compound as one of your products does not change the fact that it is still a decomposition reaction. Yes. Just because you got compounds as your products it's still decomposition. All right. And you have some examples here. If you have a metal carbonate, which you do, calcium carbonate, it can decompose into a metal oxide, in this case, calcium oxide, and carbon dioxide gas, CO2. All right. There is bases can also decompose and create metal oxides. Here you have a metal oxide, sodium hydroxide, breaking apart and yielding a metal oxide, which in this case is sodium oxide, Na2O, and water, H2O. Some unstable acids can decompose, and this time, instead of a metal oxide, it will create a non-metal oxide. For example, carbonic acid decomposes easily at room temperature into carbon dioxide, which is a non-metal oxide, and water. Any questions on these? And you can easily see that they are compounds. My products for all three reactions are compounds, okay? Decomposition reactions don't always break up into elements. They can break up into smaller compounds, into smaller versions of the original. All right. Let's check out what's going on with Mr. Anderson. Mr. Anderson with Bozeman Science. Play.
Hi, it's Mr. Anderson. This is Chemistry Essentials video 29. It's on synthesis and decomposition reactions. If I were to ask you which of the two reactions you see on the left is a decomposition reaction, the tendency is to choose the rusting railroad car. The reason why is it looks like it's breaking down. But if you think about it, what is rust? Rust is the combination of iron and oxygen. And so this is actually a synthesis reaction. So if we ever take atoms and molecules and combine them together to make a new compound, then we've got a synthesis reaction. So what's an example of a decomposition? The breakdown of water into oxygen and hydrogen gas is going to be an example. And so if we take atoms or molecules and we combine them together to form a new compound, we call that a synthesis reaction, making something. Likewise, if we take a compound and break it down into atoms or molecules, we call that a decomposition reaction. Lots of times that'll generate a little bit of heat. We can use both of these reactions in the chemistry lab to do simple stoichiometry and practice our lab techniques. It's a synthesis reaction where we're taking atoms and molecules and combining them together. So let me give you a couple of examples. Let's say we take magnesium, get it a little bit hot, and then allow it to combine with oxygen. It's going to make magnesium oxide. And so when it's done, you're going to have a new solid that's created. We're taking a solid and a gas, and we're making a new solid. Another example of a synthesis reaction could be the carbonation of water. So this is me adding a little bit of carbon dioxide to my soda stream at home. And what's going to happen inside there is that the carbon dioxide is going to combine with the water and it's going to make carbonic acid. So that carbonic acid is going to lower the pH to around 4 and it's going to change the taste of that carbon. What's decomposition then? It's when we're taking a compound and breaking it down. So here's an example. If we take sodium acid and break it down into sodium metal and nitrogen gas, that'd be a decomposition reaction. One reactant and two products, it's a good idea that this is called a decomposition reaction. Here's an example of this actual reaction. Well, this was used in early airbags. And so what you can do is you can put some sodium azide inside the bag right here. It's totally stable, but if you add a little bit of heat to it, so there's an igniter inside there, it's going to quickly break into sodium and nitrogen gas. And then nitrogen gas is going to fill up the bag. Now you can imagine a bunch of nitrogen in there is not a good thing. That's how they react as well. So they also put chemicals in here. Another example could be right here, taking hydrogen peroxide, and then I'm simply adding a catalyst to it. I'm adding an enzyme that's found in yeast. And so the yeast isn't part of the chemical reaction, it just serves as a catalyst. So what I can do is I can add hydrogen peroxide to it, seal it up, and I can give it a little bit of a shake. And what it's going to do is it's going to break down into water, and then it's going to break down into oxygen. And that oxygen is going to fill up the bag. Now, if you feel the bottom of the bag, it's going to get warmer and warmer. The reason why is that we're releasing energy as we break those bonds and form new bonds to the point where it can eventually explode. So sometimes we have to learn a little bit of that gas. So did you learn the difference between a synthesis and a decomposition reaction? Hopefully. In this one, when we're burning magnesium, we're combining it with oxygen. That's going to be a synthesis reaction. And could you do simple stoichiometry? Well, one way to do it would be to weigh the magnesium to start. You can put it in a crucible, heat it up, and then we can weigh it when it's done. We can figure out the mass of the products, and we can work backwards to figure out how much oxygen is actually in it.
Always helpful, sir. Okay, so let's continue our presentation. All right, so we're going to start with a sample problem, which I already have on Jamboard ready to go. It says here, it says in our sample problem, when an electric current is passed through pure water, it decomposes into its elements. Write the balanced equation for the decomposition of water. Okay, so we're breaking apart water. Everybody knows the formula for water, right? What's the formula for water, guys?
H2O.
For sure, H2O. Everybody agree? I agree.
Yeah.
All right, so if it's going to break apart, what's going to break apart to? What is it going to break apart into? What do you think?
H and O.
H and O, hydrogen and oxygen. But do these elements, when they break apart, do they break apart into individual atoms? Or, well, yeah, yes. But my question to you, Mr. Jeremiah, is does this element stand alone, just the way you see it? Or do they exist in another form? And I'm going to show you. Or do they exist in this form right here? Is it a part of the diatomic elements?
Yes.
Yes. So we're going to change the formula for hydrogen and we're going to make it look like this. We're going to change the formula for oxygen and we're going to make it look like this, right? Because these elements, when they break apart, they always break up into this form, okay? Into a diatomic element. So we're going to go into Jamboard and we're going to add the fact that we have two of each. All right. So we're halfway done. We are halfway done, but we're not completely done because what do they want? What's the actual question?
To balance it.
To balance it. And we've been practicing balancing, right? All right. So let's do this. My elements, what are my elements present? Oh,
H and O.
very good. Okay. How many do I have on the left of hydrogen? Everybody else agree? I agree. I definitely agree. Okay? You can see that the 2 for hydrogen is here, and we always have an imaginary 1 that's hanging out after this element. All right, very good. On the right, how many?
2H and 2O.
You can easily see the subscripts for each, right? You can easily see the 2 for hydrogen and the 2 for oxygen. So let's do that. Okay. How are you going to start balancing? You're going to start here? Or you're going to start here? If you would definitely start with oxygen. Does everybody agree? Does everybody agree with Jeremiah when he says that we should start with oxygen? I don't see anything from Oscar, Diamond, Or Mr. Irvin? What do you think, Irvin? Oscar says yes. Should we start with oxygen? For sure, right? Thank you, Ms. Diamond, Mr. Oscar. I appreciate it. Okay, what's the plan? What do I need to multiply in order to balance? Okay, but what do I need to multiply by? What goes in the blank here? 1 times 2, right? I got a 1. I need to multiply it by 2 in order to balance. Oops, I want to do it in a different color. I always like to do it in different colors. Okay. I need to multiply it by 2, right? Why? Well, it's all because I need these numbers to match, right? Before they did it. Now they do. So my question to you is, should I put it here or shall I put it down here? What's the rule? Ooh, is that correct? Is that correct? Do we change formulas when we're trying to balance? Or is it supposed to be in front as a coefficient? Do we change formulas when balancing? What's the number 1 rule? Never change the formula when you're trying to balance, okay? Keep that in mind, guys. Never change the formula. If you're going to balance, it needs to go in front of the compound, okay? I did that on purpose, okay? I wanted to see if I was going to confuse anybody. And sorry, Mr. Jeremiah, you were my victim this time. All right. Now, was oxygen the only element that got affected by this 2 that we put? No. We also affected the hydrogen, right? When I multiplied the oxygen so that I can have that 2, I also multiplied hydrogen by 2. All right, and that's going to change things, right? It's going to change it because look, now I have a 4 on the left for hydrogen. That definitely does not match the right side. What do I do to make it match? What do I need to multiply in order to make 4? What goes here? What goes in the blank? A 2. Right. Okay. Let me ask you another tricky question. And this is for everybody, not just Jeremiah, but Jeremiah is helping me. Okay, Mr. Jeremiah, do I do this or this? Where does the 2 go? For hydrogen or for oxygen? Where shall I put it? For sure. I multiplied hydrogen by 2, so that coefficient needs to go in front of hydrogen. All right? Now, my numbers on both sides are good to go. And my final answer that I'm going to submit, or that we're going to submit, is right here. That is a balanced equation for the decomposition of water. Okay? What do you guys think? Was that hard? Was that hard? Not really. It's just time consuming, right? It's time consuming, but not difficult. Okay? It's never difficult. It just takes time. All right? Let's look at Pear Deck and verify if our answer is correct. Look at it. Perfect. We have 2 moles of water. We have 2 moles of hydrogen, 1 mole of oxygen. Is that the same thing we got? Yup. Great teamwork, guys. Great teamwork. Great job. I'm really enjoying this class. Really. I enjoyed it last semester, and it's just getting better and better every day. Okay. The only thing that we forgot to put was the abbreviation for electricity, because electricity was used in the decomposition. So we have to give it credit. But that's not a very big deal, okay? I won't take too many points off if you forget to put electricity. All right. Any questions on the sample problem? Any questions on that one? All right. Paired deck question number 2. This is now on you. Write the skeleton equation and balance the following decomposition reaction. So first you need to write the skeleton equation and then you need to balance. So you're going to do 2 things, 2 skills. All right. So first off, you got nickel 3 oxide decomposes into nickel metal and oxygen gas. Oh no, let's see, what shall we do? Well, nickel 3 oxide is an ionic compound, so I need 2 pieces of information. I need the symbol and the charge for both of these elements, right? So I'm going to go into the valence sheet, our reference material, right? Our reference material is here. We need to find nickel. Nickel. Right here. Everybody sees nickel? Nickel has a symbol of Ni and either a charge of +2 or a charge of +3. Which one are we dealing with when you see nickel 3 oxide? What's my charge? +2 or +3? +2 or +3? What's my charge for nickel? I know the symbol. Oh, you know what? Let me do another color. I know the symbol is Ni, but very good. It's a +3. Why? Because of the Roman number. Everybody sees that Roman number? The Roman number helps us determine that we are dealing with nickel with a 3 charge, a +3 charge. Oxygen, right? Oxide is oxygen, an element. Oh, we work with it a lot in this class. Everybody see it? The symbol is O. The charge is -2. -2. Okay? So let's move that over. O with a -2. Okay. I need you to start on Pear Deck, somebody writing the correct formula down here for me. Can somebody write the correct formula now that you have the symbol and the charge for nickel 3 oxide? All right, there we go. There we go. Ni, small I, right? Put a dot on top of it. Okay. But show me the formula. You don't have to write the charge. We already know the charge. Everybody has it. It's right here. Show me the formula. What happens if this crosses down and this crosses down? What's going to be my formula? Remember, they switch. The 2 goes on the bottom of nickel and 3 goes on the bottom of oxygen. Can you switch them, please? Try your best. And don't worry about the handwriting. Very good. I know it's hard to draw with your mouse. O, and then what's going to come after? A 3. Remember, decomposes means that we have an arrow. We have our yield sign. Draw my arrow. And it's going to give us nickel. What's the symbol for nickel? Nickel by itself. And means the plus sign, right? And means the plus sign. Oxygen gas. Oxygen gas. If somebody wants to join, this person. I don't know who it is. And then remember, oxygen is a diatomic element. This is the formula. This is our formula for oxygen. If it always says oxygen gas, you're going to use this formula. Hydrogen gas, nitrogen gas. These are the ones you're going to use. Okay, guys? Very good. Perfect. Okay. Now that we have the reaction, because you guys wrote it for me, I'm just going to copy what you wrote. So nickel 2 oxide decomposes and breaks down into nickel plus oxygen. So that's the skeleton equation. So we're done with half of the question, right? We now need to balance. Okay? I can help you with that. What's my list though? What's my list? What are the elements involved here? What do I write down here under the yield sign? What do I write? What are the elements in this compound? Nickel and oxygen. Very good. Ni and O. Okay, Miss Diamond. How many nickels? How many oxygens? Or anybody? How many nickels on the left? How many oxygens on the left? Thank you. How many oxygens, Miss Diamond? Miss Di. I'm going to call you Princess Di. 3. All right. Now that we got 2 and 3, what about on the right side? What about the right side, Miss Di? Miss Diamond. Very good. 1. Oxygen. Jeremiah, you left me. 2. Great. Okay. Now, anytime you have more than one odd number, you see the 1, you see the 3, always start with the bigger odd number. In this case, the 3. Okay? Anytime you have a 3 and a 2, you're going to do a switcheroo. You're going to put the 2 and multiply. You're going to put the 2 and multiply with the 3, and you're going to put the 3 with the 2 and multiply. You're going to switch them. Okay? Anytime you have a 2 and a 3, you switch, and they're going to balance. Okay? Just watch. Okay, so I'm going to multiply here by the opposite. Oops, not that. I'm going to multiply by the opposite number. And for the left, a 2. For the right, a 3. And check out how they balance. Right? Everybody got me there? Okay. So where does the 2 need to go? On the left. In front of the compound, right? So we're going to put the 2. Oops. I always like to use red so you can see where the numbers are going. And then for oxygen, on the right, we're going to put a 3, right? Okay, so far so good. But who got affected on the left when I put the 2? Who else got multiplied by 2? Nickel also got multiplied by 2, right, Miss? Right, Miss? So we're going to put a 2 here. I'm going to multiply, and I'm going to change my reaction because now, check this out. My oxygens are balanced, but check out my nickels. They're not balanced. So what am I going to do? What am I going to do to the right side to make them balance? Oscar, I haven't heard from you. Irvin, what am I going to do? If I have a 1 and I need a 4, what's the plan? I have a 1 and I need to change it into a 4. What's the plan? You cannot add. You can only multiply. You're going to multiply by 4. Okay? You see how the only thing we can do is multiply, Mr. Oscar. we're going to multiply the 1 by 4 so we can make 4. Okay? I don't think you were here the day that we covered this, so I want to make sure you understand. You see how we did that? Oofa. Okay. And I'm going to put a 4 here. Do you see? 4 and 4. 6 and 6. This is my final answer. Oops. I'm going to do it in another color. That is the skeleton equation balanced. Okay? You see that, Oscar? We can only multiply when it comes to balancing. We can never add. We cannot divide, we cannot subtract, we cannot add. The only possibility is to multiply. Questions, guys? Questions? Any questions on this? Guys, we're going to be practicing this balancing thing probably for the next week. Okay? Probably for the next 6 weeks. I don't know, but definitely at least another week or 2. Okay? So don't worry. You're going to get more practice, Oscar. You're going to get more practice. So don't worry. Don't worry. Be happy. All right. We don't have time for the video. I think this is like a 5-minute video, and we still need to do the question. So let's move on. A definition of decomposition reaction and example reactions were given, right, throughout the presentation. Your review questions. What is a decomposition reaction? What is usually needed for a decomposition reaction to take place? Are elements always the product of a decomposition reaction? All right.